Hello everybody. So in the last video, we looked at improper integrals of type 1, which were integrals from a to infinity or minus infinity to b and so on. So that was when the graph of the function extended infinitely far in the horizontal direction. So now we're going to look at improper integrals of type 2, which is when the function has an infinite discontinuity somewhere in the region where we're integrating. And this is when the graph of the function goes infinitely far in the vertical direction. Okay, so let's see how it plays out. So here is the definition. Let's suppose we have a function which is continuous on our interval, except maybe at the right endpoint, b. So it has an infinite discontinuity at b, let's say. Then we define the integral from a to b of f. How do we do that? Well, b is the bad point. All we do is we replace b by some point t. We integrate from a to t, and since t is less than b here, this one makes sense. We integrate from a to t, we get an answer in terms of t, and then we take the limit as t tends to b from the left. So remember, that's what the limit as t tends to b minus means. We just means we let t get closer and closer to b from the left. Okay, and if this limit exists as a finite number, we say that the improper integral converges, and the value is this thing on the left. And similarly, if there is an infinite discontinuity at the left endpoint a, so if our function is continuously in interval except possibly at a, whereas there is an infinite discontinuity, then we replace the bad point a by some number t, which is a little bit bigger than a. We integrate from t to b, which is possible using all the tools we've already seen. We get an answer in terms of t, and then we look at what happens as t gets closer and closer to a. And if that limit exists, we say that's the improper integral, and we say the improper integral converges. Okay, so as we said, if these limits exist as finite numbers, then we say the improper integral converges, and if they do not exist as finite numbers, either because they don't converge at all or they go to infinity or minus infinity, then we say the improper integrals diverge. Okay, and as you might expect, there is also a question of what happens if the infinite discontinuity is in the middle. So we talked about what happens if they're on either side. If it's in the middle, then we just chop up into two pieces. So if we have a function that's continuous everywhere except maybe at some point in the middle where there is an infinite discontinuity, then we just chop at that point c, and then we end up with two integrals, say from a to c and from c to b. If the infinite discontinuity is at c, then if we're looking at a to c, this is an interval where it's on the right, and then c to b, that's an interval where it's on the left. And then we handle each of those separately. So these separately are improper integrals, as on the last slide. And then if they both converge, we just add the result to get the integral from a to b. If either of them diverge, then the improper integral diverges. So for these ones where the infinite discontinuity is in the middle, we need the improper integral to converge on both sides. Okay, so let's see some examples how it works. So a pretty typical question. Let's try to decide whether the integral from 2 to 5 of 1 over the square root of x minus 2 is convergent or divergent. If it's convergent, find the value. So if you see language with integral and converge or diverge in the sentence, then that's a pretty clear sign that it's potentially an improper integral. So you have to understand why. So the limits are not infinity or minus infinity, so it must be potentially improper of type 2. Okay, and if we look at what happens at the endpoints, for instance, at 2, the bottom is 0. So we have a fraction where the bottom is 0, the top is 1. Okay, this is going to go to infinity as we approach 2. So this has an infinite discontinuity at 2, which is on the bottom, on the left. Okay, so we have to replace 2, which is the bad point, by t, and look at what we get in terms of t. So we're integrating from t to 5, our function. If we write that as x minus 2 to all to the power negative a half, then you could, for instance, apply an easy substitution, or just keep in mind that linear compositions keep integrals nice and easy. The antiderivative is 2 times the square root of x minus 2. That's an easy antiderivative. It's definite with limits to t and 5, so we have to plug in t and 5. If we do that, we get 2 square root of 3 minus 2 square root of t minus 2. Okay, so we got a value of our integral in terms of t, but that's not what we wanted. We want to understand the integral from 2 to 5. So now we have to look at what happens as t approaches 2. So what happens as t gets closer and closer to 2? We look at the limit. Okay, so by definition, we're supposed to be looking at the limit as t approaches 2 from the right of our integral. We just calculated our integral in terms of t. So we're looking at the limit as t approaches 2 from the right of 2 root 3 minus 2 square root of t minus 2. Okay, 2 root 3 is just a constant. It doesn't depend on t, so it just stays. If we look at if t approaches 2 from the right, t minus 2 is going to approach 0. So also the square root of that is going to approach 0. Multiply it by 2, it doesn't make a difference. It still tends to 0. So the second piece is tending to 0, and we're left with 2 square root 3. Okay, that's a finite number, so the improper integral converges to 2 square root 3. And this is pretty much, this is indicative of what are the steps in any problem like this, right? Determine whether an improper integral converges or diverges, replace the bad point by t, work out the answer in terms of t, and then take the limit. Right, it was also similar for type 1, where we were integrating up to infinity. We replaced infinity by t. We worked out the answer in terms of t. We let t go to infinity. Here, the bad point was 2. We replaced 2 by t. We work out the answer in terms of t, and then we let t go to 2. So it just kind of splits improper integrals into two problems that we already know how to do. One, which is calculating traditional regular old integrals with nothing weird happening in them, and then taking limits, which we also know how to do from Calc 1. Okay, here's another example, maybe it's slightly more complicated. Determine whether the integral from 0 to pi over 2 of secant x converges or diverges. So the steps are going to be the same. So firstly, we have to see how this is an improper integral. So keep in mind that secant is equal to 1 over cosine. So this could go to infinity when the bottom is 0. So when cosine x is 0, okay, that does happen somewhere in our interval. That happens at x equals pi over 2. So there is an infinite discontinuity at x equals pi over 2 because then cosine is 0, secant is going to infinity. Okay, so we have to replace pi over 2 by t, work out the answer in terms of t, and then look at what happens as t tends to pi over 2 from the left. So we first calculate the integral from 0 to t of secant x. This is kind of a standard one or a tricky one. It's less often used, but I recommend having it on your formula sheet. It's the ln absolute value secant x plus tan x. So that's our antiderivative. We have to plug in 0, plug in t. Plugging in t is easy. If we plug in 0, the inside secant is going to be 1, and tangent is going to be 0. So we end up with ln of 1, and ln of 1 is 0. So that term disappears. So we're just left with ln absolute value secant t plus tangent of t. Okay, and then we're supposed to look at what happens to that as t tends to pi over 2 from the left. So it looks like a very complicated limit, so let's break it down. So if we think about what's happening starting from the inside and working our way outside, so secant is 1 over cosine. So as t is getting close to pi over 2, cosine is going to go to infinity. So 1 over cosine is going to go to 0 rather. So cosine is going to 0, 1 over cosine, which is secant, is going to infinity. So secant t goes to infinity. And then similar story with tangent of t. As t goes to pi over 2, tangent is sine divided by cosine. Sine will be going to 1, cosine will be going to 0. So this is also going to go to infinity. So the inside, both terms are going to infinity, so that sum goes to infinity. Okay, we take absolute values, that doesn't change anything. Ln of that still doesn't change anything. So this limit is going to be infinity. Okay, so to conclude, this improper integral diverges. Right, we replace the bad point, which was pi over 2 here, by t, work out the answer in terms of t, take the limit as t goes to whatever it was supposed to be going to. In this case, pi over 2. Okay, maybe one word of warning, which is with splitting, please be very careful. So for instance, does the integral from -1 to 1 of 1 over x converge or diverge? Looks pretty harmless. So remember, so here, why is it improper? It's improper because at x equals 0, which is in the middle, the function has an infinite discontinuity, right? 1 over x goes to infinity. If x goes to 0 from the right, it goes to minus infinity. If x goes to 0 from the left. So with these infinite discontinuities where the bad point was in the middle, we were supposed to split into two one-sided improper integrals and handle them separately. So we are supposed to split into 0, 1, and -1, 0. So let's forget completely everything else and just focus on 0 to 1 of 1 over x dx. So it's improper. The infinite discontinuity is at 0. We are supposed to replace 0 by t, work out the answer in terms of t, and then let t go to 0. So if we replace 0 by t, we work out t to 1 of 1 over x. Okay, the antiderivative is ln absolute value x. If we plug in 1, we get ln of 1, which is 0. If we plug in t, we get ln t, and then of course we have to subtract, so we get minus ln t. Okay, and then if t goes to 0 from the right in that, then we're looking at the limit as t goes to 0 from the right of minus ln t. Remember, if t is a very, very small positive number, then ln t is a very large negative number. And then we reverse the sign, we are going to get plus infinity. So do remember the graph of ln t, right? As t goes to 0 from the right, t is a very small positive number. ln of t is going to be a very, very large negative number. Then we flip the sign, we get a large positive number. This limit is going to be plus infinity. Okay, and straight from here, and without even doing anything else, we can say that the improper integral diverges, both the improper integral from 0 to 1 and the improper integral from -1 to 1. Remember, we said that this improper integral, where there is a bad point in the middle, where there is an infinite discontinuity in the middle, the only way it can converge is if both of the one-sided improper integrals converge. In this case, okay, even the right-sided improper integral does not converge. Okay, so this is divergent. Okay, what is the warning? Let's suppose that we were kind of being naive and we were hoping for the best. Let's suppose that we don't see that it's an improper integral of type 2. So we want to just integrate -1 to 1 of 1 over x. Suppose we try to use, say, fundamental theorem of calculus, which would mean We find the antiderivative, which is ln absolute value x, and then we're supposed to plug in the endpoints 1 and -1. So if we go ahead and plug in 1 and -1, we plug in 1, we get ln of 1. We plug in -1, we get ln absolute value of -1. Absolute value of -1 is 1. So we have ln 1 minus ln 1. Okay, and both of those are 0, so we might suspect this is 0. So this is a huge mistake. Please don't do this. The thing why this is not acceptable is that fundamental theorem of calculus only works for functions which are continuous on the closed bounded interval. So please don't just jump in and use fundamental theorem of calculus. Take a second, try to decide whether it's an improper integral. If it's clearly, if you see infinity or minus infinity in the limits, then it's going to be improper integral of type 1. Check and make sure that the inside is not going to infinity anywhere in the, it doesn't have any infinite discontinuities anywhere where we're integrating if the limits are finite. For instance, -1 to 1. You want to look and make sure that the function we're integrating doesn't have any infinite discontinuities. For example, 1 over x has that infinite discontinuity at 0. Okay, so let's wrap things up by looking at the comparison theorem. So, quite often we want to understand whether an integral converges or diverges, but maybe it's kind of hard to compute everything, or we don't want to compute everything. What could be another way? One way is to compare it to something we already understand. So let's suppose we have two functions, f and g. They're both positive, and g is less than f. So we have two positive functions. One is a small function, one is a large function. G is smaller than f. For x larger than a, let's say. Okay, then it's true that if the improper integral, so here everything is written for type 1 improper integrals, but there is a similar result for type 2 improper integrals. So if the integral of f converges, then the integral of g converges. So this is saying that if the large function, the improper integral converges, then also the improper integral of the small function converges. So here be very careful, right? We're saying g is less than f, so that here we're saying the large function converges, then the integral of the small function converges. So, we want to be very careful when we apply this, but what is the intuition? The intuition is that these improper integrals are representing areas, since the functions are positive, there are no signed areas. So these are representing areas, and g less than f is saying the graph of g is below the graph of f. And the improper integral of f converging is saying that the area under the graph of f is finite. So here we are kind of saying, if the area under the graph of f is finite and the graph of g is below the graph of f, then the area beneath the graph of g must be finite. So it kind of makes sense in terms of areas as well, but that's just the intuition. Okay, and then going the other way, if the integral of g diverges, then the integral of f diverges. So we're saying if the small function diverges, then the larger function the integral must also diverge. So here we're saying that, if the graph of g is below the graph of f, and there is an infinite area beneath the graph of g, then there must be an infinite area beneath the graph of f, for instance, just intuitively. Okay, and there, as I said, there is a similar theorem for type 1 and type 2. So please be very careful of the way that the logic goes here. If g is less than f and the integral of f converges, then the integral of g converges. If the integral of g diverges, then the integral of g diverges. If the integral of g converges, then we can't say anything about the integral of f. It might converge or diverge, it just depends. So the logic here is very important, right? If I have a small function and a large function, and I know the small function converges, I can't say anything about the large function. It just depends. Okay, so for example, let's see an easy example. Does the integral of sine squared x times e to the minus x converge or diverge? This is an improper integral of type 1, so we want to maybe use the comparison theorem. Comparison theorem is useful if we can't compute everything. Okay, this looks like it's very hard to integrate if we can even do that at all. So if it looks like we can't integrate it explicitly, we might want to use a comparison theorem. Okay, what should we compare it to? Well, we know that that sine and cosine are always less than 1. So one easy way to get an inequality is to replace sine by 1 if you're going up above, or sine by -1 if you're going below. Or here, if sine is less than 1, then sine squared. If sine is between -1 and 1, then sine squared is between 0 and 1. Okay, so if we just use the fact that sine squared is bigger than 0 and less than 1, and then we multiply that by e to the minus x, sine squared x is less than or equal to 1, so sine squared x times e to the minus x is less than or equal to 1 times e to the minus x, so e to the minus x. So now we have positive functions, and we have a small function and a large function, so we might hope to use comparison tests. And it's easy to check that the improper integral from 0 to infinity of e to the minus x converges. For instance, we replace infinity by t, work out the integral from 0 to t of e to the minus x. It's an easy integral to do. Take the limit as t goes to infinity, you'll see that it converges. I believe it's to 1. Okay, so the improper integral of the larger function converges, hence the improper integral of the smaller function converges. So this is an example with a comparison test. Okay, we'll do more examples with the comparison testing class and talk about this some more, but thank you for watching. See you next time.